Okay, we are at the top of the hour, so I think it's time to start with this webinar. Let me introduce myself. I'm Davide Villa. I'm the Chief Revenue Officer at Xinnor, and together with me, I have the pleasure of having Markus Hilger, the Senior HPC Engineer at MEGWARE.
Yeah, hello.
So the webinar of today is to present how MEGWARE was capable of implementing a storage cluster at the FAU University, the Helma storage cluster, based on commodity hardware, Xinnor software, and Lustre. And this storage cluster managed to get into the IO500. During the presentation, we will go into details on the tuning that were implemented, the details of the architecture, and whatever was implemented by MEGWARE to achieve such an amazing result. If you have any question, you can ask your question by writing them into the chat box on the right-hand corner of your screen, and we will answer the question at the end of the presentation. So let me start by showing who is the Frederick Alexander University. Frederick Alexander University hosts one of the 9 national high-performance computing in Germany, the Erlangen National HPC Center. And at the beginning of this year, the HPC Center implemented a new compute cluster called Helma. And this compute cluster is made of almost 200 AMD EPYC dual socket and almost 800 NVIDIA H100, H200 GPU, which makes this HPC cluster one of the fastest supercomputer in Germany, actually the fastest supercomputer owned by a university, and also one of the fastest worldwide, since it managed to get in 51 position on the June top 500 list. Frederick Alexander is not a new name for Xinnor and MEGWARE. We actually deployed a storage cluster already in 2024. It was an all-flash storage cluster. What is new is that now we managed to make it even faster, and we had the high availability, no single point of failure. So if we look at the storage cluster, which is also called Helma, it's based on Lustre community version 2.16.1. It is 6.4 petabyte of raw flash, which is about 4.9 petabyte of usable capacity on PCIe NVMe Gen 5. And it's based on just 10 systems. Those are a Celestica SC6100, which you can call a cluster in a box or a storage bridge bay. Those are basically 2 servers in the same box sharing the same 24 NVMe drives. And it's designed for high availability purposes. And then one of the most critical components into this equation is our software, xiRAID Classic, which sit upon the hardware and below the file system to provide data protection in 2 different ways. For the metadata, MEGWARE implemented RAID 10 mirroring data protection. And for the data, it was a more cost-effective RAID 6, 8+2. xiRAID Classic comes with an agent to do smooth integration with pacemaker and chorusing, which enabled to build a full highly available storage solution. After implementing the storage cluster, MEGWARE ran the IO500 benchmark. For the people who don't know what the IO500 is, IO500 is an industry benchmark. Everybody can can run this benchmark and submit the result of the benchmark to the IO500 committee. And 2 times per year, they release the new list, they update the list based on the result that has been submitted. So if we look at this list, you will see that the Erlangen National HPC Center is now listed in the 3rd position with the implementation done by MEGWARE with Lustre, and with the best score when it comes to traditional parallel file system. Only DAOS was able to achieve a higher performance, but for much larger type of deployments and much more complex type of deployments. But performance is not everything. So if we look at, if we deep dive into the IO500 list and we focus on the traditional parallel file system, like Lustre or Weka in this case, you will see that to get high performance, they need much more hardware. So not only the Helma cluster is extremely fast, but it's also one of the most efficient in terms of performance per hardware. There is not a ranking in this space, so we're just driving to the conclusion based on the information on the IO500 list. But it's fair to assume that not only it's the fastest, but it's most likely the cheapest as well on the overall list. And if we look at the architecture of this deployment, you see that, as I said, it's based on 10 Celestica systems, each of them made of 2 independent nodes, each of them equipped with 2 times 400 gigabit InfiniBand connectivity, and each of them seeing all the 24 drives. In this case, we use a Phison drive. That was a decision from MEGWARE, and they selected 6.4 terabyte for metadata and 30 terabyte more cost-effective dollars per terabyte, but less performing from a write performance standpoint for the data themselves. So with this, I think I can hand it over to Markus, who will go into the details of this deployment.
Yes, thank you, Davide, and I will keep on going and tell you a little bit more about how this system is actually configured, what kind of tunings we applied, and also some tips and tricks to, improve your maybe IO500 score. And some of the tunings are probably specific to this deployment, but most of them should apply to basically all kind of like Lustre-based deployments. So hopefully there's also some like useful information for maybe your existing deployments as well. So as Davide already told you, that we have like these kind of building blocks based on the Celestica SC6100 systems. In fact, you can use different SPV systems as well. We went for the Celestica one because we tested it and it was performing quite well. And in the front, and so that's basically behind this black cover you see on the bottom right corner, we have these 24 NVMe drives. And the special thing about these servers is that they have dual port NVMe drives and dual port NVMe slots. So meaning each NVMe drive has basically 2 PCI 5 X2 lanes. And then one X2 lane is connected to the first node, and the second X2 port is connected to the second node. And in this 2U box in the back, you have basically 2 nodes, 2 x86 nodes, and they can then access simultaneously all 24 NVMe drives in the front. And this we basically use to achieve like the high availability and failover of RAIDs and file systems and so on. One of these building blocks here has, as Davide already told you, like 20, 30 terabyte drives, 1000 Pascal drives, which have like quite good performance. They're actually pretty much like one of the fastest PCI 5 devices you can get right now. There's 14 gigabytes a second read per device and 7.5 gigabytes a second write per device. But because we only have PCI 5x2 to one single server, we actually have to create two NVMe namespaces, and an NVMe namespace is basically like similar to a partition somehow, like not the same, but similar, where you can then have like basically two devices out of one. And then you can access the single device from both servers simultaneously. So you get 2 times the X2 bandwidth to get the full PCI 5 X4 bandwidth to the drive. Because PCI 5 X2 is only roughly like 8 gigabytes a second. And if we hit up to 14 gigabytes a second read on a single drive, we would be limited by this X2 PCI 5 bandwidth. So that's why we need these like two namespaces to be able to reach like the full read performance of a drive. And if you combine all this together, and also together with the network interfaces, so I forgot to talk about the network interfaces. So each server here has 2 times NDR 400 InfiniBand NICs. And because we have two servers, in total we have on the single server 4 NICs with NDR 400. So this is roughly like 200 gigabytes per second of bandwidth. And if we look at the performance numbers on the left, these numbers are with the actual Lustre file system and actually measured from a client. So all the overhead you have in the network and file system layer and RAID layer and so on is included in this performance number. As you can see, we almost reached the network lane speed with like roughly 100 gigabytes a second read on a single 2U box and roughly 80 gigabytes a second sequential writes. And sequential writes are slower because of the slower write speed of the NVMEs and also because we obviously have parity of RAID and stuff like this. So it's expected to be a little bit lower than the read speed. And then for high availability, we have pacemaker co-resync, and I will come to this later on. So first of all, now let's talk about some of the settings we apply to reach this performance. I will start with like low-level settings like BIOS settings and so on. And later on, I will also cover like Lustre tunings and also IO500 specific settings. So first of all, the BIOS settings. So we disabled CNP states because usually for low latency storage, you don't want to have any like CNP and sleep states and whatsoever, because you want to have like the lowest latency possible. And the amount of energy you need to with like disabled CNP states is not too much because all the NVMe drives and so on usually consume way more than the CPU anyways. On top of that, we disabled any virtualization and abstraction layers if possible, because we don't run any VMs or anything like this. It's all like fully bare metal. So we want to disable as much as possible. Then IOMMU is enabled because on the AMD platform, you actually need it to run X2 APIC mode, which we do. And for the NUMA setup, we choose NPS1, which basically means you have like a single NUMA domain per CPU. And you could also like experiment with NPS2 or 4. But for simplicity, we just stick to NPS1 because we didn't see any huge performance gains with anything else. Now there are also some important kernel parameters we had to use, or we choose to use to increase the performance. So first of all, because we have to use IOMMU, we set it to PT, which means pass through. So again, it basically disables the functionality somehow. Again, to lower the number of abstraction layers we have. Furthermore, we don't need any native NVMe multipathing because we don't have multiple paths. We only have like a single path from a single server to a single NVMe. So that's why we can disable the native NVMe multipathing, which can also cause like performance degradation in some cases. And last but not least, there's a special setting we had to use for this specific platform. It might not be required on other platforms, but we saw that we had some PCI performance degradation, so we are not able to achieve the full read speed of the drives. And we figured out that this was due to the PCI Express maximum payload size, which was set by the BIOS to 128 bytes. But the drives were actually able to do 512 bytes payload size. So with the PCI equals PCIe bus performance kernel parameter, you can tell Linux to try to increase this PCIe payload size to the maximum possible. And again, this helped us to achieve like the full speed of the NVMe drive, which is basically declared on the data sheet. So yeah, for I saw this on the other systems that's already 512. On some other, it was also 128 and so on. I mean, you can check with LSPCI if you are affected as well, but like for the specific system, we needed this. And all the other settings are mostly default, so there are no like special QD settings, CTL settings, or anything like that, because the kernel and BIOS settings pretty much set everything we need already. So next, I want to focus a little bit on the xiRAID configuration itself, and also the high availability configuration, how we did it. So just as a short recap, again, we have like these 24 NVMe drives in a server, and they are all connected with two PCIe lanes. That's why we need like two namespaces on each NVMe to get like the full PCIe bandwidth. And then we have like RAID 6 and RAID 10 configured. And here on the picture, you can also see that in the back, you can see the two servers in the back. And here on this picture, you can actually see the RAID layout, how it looks like. So you can see that we have node 0 and node 1. Yeah, this is like a single building block. And then we have our 24 NVMe drives. And NS is for namespace 1 and 2. So we have two namespaces per NVMe drive. And then we actually have for the metadata array 10 out of like 4 namespaces and actually 4 NVMe drives, which is MDT0 on node 0. And then another RAID 10 on node 1, which uses the same NVMe drives, but the second namespace this time, which is like a lighter purple MDT1. And for the OSTs, it's pretty much the same. So this time we use RAID 6 with 8+2, so 8 data drives and 2 parity drives. So in total we have 10 drives. And again, we have on node 0, OST 0 and OST 1 with 10 drives each. And on the second namespace on node 1, we again have the very same NVMe drives, but the second namespace for OST 2 and 3. And in like if everything is working fine and as expected, OST MDT0, OST 0, and OST 1 is mounted on node 0. And on node 1, MDT1, OST 2, and OST 3 is mounted. But in case of a failover, because one of the node fails, for instance, the other node can take over all the MDTs and OSTs and also like RAID block devices and so on from the other node. Now let's talk a little bit about the xiRAID specific tunings we applied. So the defaults are mostly fine, but you can achieve some better sequential performance if you increase the RAID strip size. So the default one is 16 kilobytes, but with most NVMe drives, you actually get the best performance if you go up to like 64 or 128 kilobytes. In this case, for the Helma system, we went with 128 kilobytes strip size, which means 8 times 128. So your stripe size is pretty much 1 megabyte. So the perfect block size to write to the file system would be 1 megabyte in this case. Then you also have to be aware of your NUMA topology. So all your RAID devices and so on should be on the same NUMA domain. You don't want to span like multiple NUMA domains for a single RAID device if possible, because we only have like single socket AMD CPUs inside these nodes. That's kind of easy. With NPS1, everything is like on NUMA domain, so that's not too hard in this case. And the last setting is SCAD enabled. So this is a special xiRAID setting because usually by default, if some application is doing an I/O request, the xiRAID engine will execute the actual I/O on the very same core the I/O request was done. So it will not switch to a different core. And this can lead to some overutilization of some cores, because applications might tend to only use some specific cores. So with schedule enabled, you can basically enable some kind of scheduler in the xiRAID engine, which will then distribute the I/O load evenly across all the CPU cores to achieve better performance. And especially with Lustre, this seems to help to reach better performance. Here you can actually see the settings we used. This is an extract of the system, basically. So as I said, like we have the MDT1 with RAID 10 with 4 drives. Yeah, this is the output of the xiRAID, basically. And we have scheduling enabled. And we set some specific CPU allowed cores. So these are like CPU core IDs, which are allowed to access the device, basically. So all the I/O requests will go through one of these core IDs, and the scheduler will choose a core based on the CPU allowed values here. And these CPU allowed values are especially tuned for this specific CPU to be basically on the same CCD or 2 CCDs in this case, to not span like multiple CCDs.
Okay, I see that Markus lost connection. Hopefully we'll be able to join. Here it is. Here he is. You're back.
Yeah, so and then we have OST, and that's pretty much the same. RAID level 6 in this time, and the strip size of 128 kilobytes. Yeah, and again, a different set of CPU cores, as you can see at the bottom. So because we don't want to have overlapping CPUs between metadata and data, we want to try to separate them so they don't interfere with each other if possible. Now a few comments about the high availability architecture. So this is purely based on pacemaker and co-sync. And on top of that, we also have like a shoot the other node in the head device configured via IPMI. So in case of one of the two servers is behaving strangely and you can't control it anymore, the other node can actually shut it down via the PMC. And as Davide already mentioned, the xiRAID classic engine includes like a pacemaker agent. So to fail over the RAID volumes, there is like a native agent for coming with the xiRAID installation you can use in a pacemaker setup. And then on top of the RAID failover, you just have like a Lustre file system mount failover as well on top of that. And then some like health checking around to fail over the OSTs and MDTs between both nodes. And now to our last topic, which is the Lustre setup and Lustre related tunings, and also the IO500 test itself, and some kind of tips and tricks for the IO500 test. So first of all, for the LNet tunings, we increased the credits a little bit because we have NDR 400, which is kind of fast. So we increased the network credits available in LNet a little bit. The default is like, as you can see here, 8 to 265 and 4, and we increased it to like pretty much twice the size. The servers also have 100 gigabit Ethernet, but the Ethernet settings we just kept as default. So Lustre is also able to mount via Ethernet in this case and this installation, because we have some of the compute nodes only have like an Ethernet connection, no InfiniBand. And here are some of the Lustre tunings we used for the IO500 run. So first of all, we enabled 16 megabyte bulk RP, like RPCs, remote procedure calls for Lustre. By default, that's 4 megabytes, but with 16, you can get some additional performance. Usually in flash-based systems, the performance uplift isn't too big, but anyways. Then you can allow some more RPCs in flight, which basically means that, for instance, especially for metadata operations and so on, you can queue some more operations via the network. The default settings are around like 8 or something like this. So you can increase this a little bit to get better metadata performance. On top of that, you can disable memory and wire checksums. So usually the InfiniBand layer itself is doing checksums, and usually you have ECC memory, which is also doing checksums. So usually everything should work fine, and you have checksums on all the layers already. So you could disable the checksums to gain some additional performance. But there could always be like a firmware bug in the InfiniBand firmware or something like this, and somehow the checksums are calculated incorrectly or something like this. And then having an additional layer of security on top in Lustre calculating own checksums is beneficial. So this we only changed for the IO500 benchmark itself, but not for production, because like the performance uplift isn't too big. Yeah, it's roughly like 5% or something like this. It depends on the CPU and so on you have in your clients, but for like a hero run benchmark, you can disable the checksums. And then we found that especially for IO500, IO hard benchmarks, which is basically a benchmark where all the client processes write to a single file. So you have like a lot of locking going on. If you artificially lower the allowed locks per client, way lower than the default Lustre settings, you actually get better performance. So yeah, we lowered this a little bit, and also the amount of time the locks are valid are lowered to like 1 second instead of the default. I think it's 5 minutes or something like this, which also helps performance a lot in this specific benchmark. And here you can see the actual IO500 settings. So first of all, if you can, try to use ODirect, like POSIX ODirect for the IOR Easy benchmark, because IOR Easy is just writing sequential data, and it's usually like perfect block size and so on, so you can use ODirect. And this way you don't have to use the kernel page cache of the client, which is usually if you have, especially if you don't have too many clients, this can usually your performance culprit in some cases. So if you're using ODirect, you go around the kernel page cache and don't use the kernel page cache on the clients, and actually achieve like better values and can actually measure the real like storage performance and not benchmark the Linux page cache on the clients basically. And furthermore, the IO500 already includes the IO500 SH start script with some Lustre-specific tunings inside, and most of these tunings are already really good. But there's one setting which is not optimal, and this is the MD test easy. So for the MD test easy is basically you have a bunch of directories with like thousands of files inside these directories, and these files are created and written. And then later on, there's stat called on these files, and they will be deleted at the end. But because all these files are in different directories, it's better to use Lustre's DNE3 feature instead of DNE2 for this specific test, because DNE2, which is the default in the IO500 SH script, is basically striping every directory across all the MDTs of Lustre. So every directory is somehow on all the MDTs, and there's a lot of communication overhead between the MDTs to during this benchmark basically. But because we have like separate folders already, we can use DNE3, which is a newer Lustre feature, which will attach a single directory to a single MDT. And this is done in a like round robin fashion. So you can distribute the load evenly across your Lustre MDTs and don't have like this communication overhead because of the MDT striping. So for the MD test easy, that's a like way better option to use. For MD test hard instead, you can use the default DNE2, which will stripe the directory, because in MD test hard you only have like a single directory with millions of files. So it's better to stripe across all MDTs. The other settings mentioned here are pretty much the defaults of the IO500 SH script. So you can leave them as is. And this is like our last slide for today. This is like the actual IO500 submission result. And here I want to highlight some of the values. So first of all, we have the IOR easy write and IOR easy read values. These are our like sequential write and read performance. And here we can see that we have more than 800 gigabytes a second write performance, and more than 1.8 like, because it's gigabytes, more than 1.8 terabytes a second read performance. So if you remember correctly, a single building block can do roughly 100 gigabytes a second read and 80 gigabytes a second write. So times 10, because we have 10 building blocks in this installation, we get exactly like this value here. So it scales linearly. On top of that, you can see that the MD test values, these are reported in IOPS, are like also kind of high compared to other like storage systems on the list, because we have all these MDTs. So each building block has its own MDT as well, or like two MDTs actually, because of the namespace splitting. And this also achieves kind of high metadata performance as well because of this. And at the very bottom, you can see the new test, which was introduced at IC 25 the first time, which is IOR random 4K easy read, which is basically a 4K random read IOPS test. And there we measured like 87 gigabytes a second, which is roughly like 23 million random read 4K IOPS. So it's not only like sequential performance is good and metadata performance, but obviously also the file 4K IOPS performance is good. And actually here we hit like a client limit. So with other benchmark tools other than IOR, I was also able to measure up to like 35 million 4K read IOPS with like these 10 building blocks. So also IOPS are like really high with this solution. And yeah, and our total score like 838, which is also compared to other systems kind of good. And all this is basically done in like half a rack. So we only have like 10 times 2U servers achieving this kind of performance, which is kind of great if you compare to other solutions. Yeah, and that's pretty much it for all the tunings and so on we applied, and yeah, hopefully you have some questions and we can answer some of them. We also wrote like a case study. You can see it on the link and the QR code, where we also describe the architecture and so on as well. So yeah, together with this, like these slides, you should get a pretty good understanding on how we did it.
Okay, thank you, Markus. I see we have many questions on the chat, so let's go through them. The first question is very easy to answer. We actually have a slide about it. Yes, both Xinnor as well as MEGWARE will be exhibiting at Supercomputing in 10 days. So please stop by our booths or send us a message if you want to book to schedule a meeting. It will be very chaotic and messy, so I highly recommend to book a meeting in advance. With this, let's go through the list of questions. I see that there are many technical questions, most of them are going to you. So the first question from Joshua. So what is the recommended value, 512B, or can you do that on a per link basis? I think this was related to...
Yes, yeah, so the recommended value is basically the highest one your hardware supports. So this depends on the NVMe drive itself and also the PCIe switches and so on below this. In our case, it was 512B, but it could be different on different systems. So you have to check with, you can check actually with LSPCI-V. You can check your actual max payload size and also the max supported payload size. And if you see there's like a difference between the maximum supported one and the actual max payload size, then you might have a performance degradation because of this.
Okay. Still from Joshua, there are questions about splitting where do you split OST 0 and OST 2 from node 0 to node 1? Shouldn't you keep within the node the OST? I think there is a misunderstanding here because the picture might be misleading. The 24 drives are not attached to a single node. They're attached to both nodes at the same time. So we're not splitting the OST between the two nodes. Okay, going on. Yeah, that's still on the same topic. You use NTB for HA. Maybe you want to elaborate a bit more. Markus,
yeah, we don't use NTB for HA, just like a failover, and there's like no caching or anything like this going on between the two nodes. They basically behave as like separate servers, and just fail over if one of the nodes fails, basically.
Okay. Then the following question from Jean Botsman. He wants to see some use cases. This is actually a use case. It's actually a case study of a real deployment. What are the university doing with so many GPU? they do a lot of things. They do AI predominantly. They do a lot of machine learning, and they do gesture recognition, genomics research. If you read the case study, there is a list of the research that are implemented by the university. And also, if you go on their website, you will see what they are experimenting on. Will you comment on read and write performance for each machine and show the performance scaling when adding storage server?
Yes, yeah, this I can comment on. So yeah, as I showed, like roughly 100 gigabytes a second read and 80 gigabytes a second write per building block. And if you add another one, it's just ×2. If you add 2 more, it's ×4 and so on. Because that's just the nature of Lustre, how it's scaling. So the more you add, the more performance you get, basically. And I mean, we tested this year's tested with 10, and it's exactly 10 times the performance, basically. And also the metadata performance is scaling because we also add metadata devices if we add yet another building block. And I can also comment on the next one. So MDS, MDT is a common cause of usual, say, DDN Lustre failures. Could you comment if the Lustre over xiRAID performs better for MDS, MDT loads than a regular setup, also with MDT on NVMe's? So yes, I know about this, and I mean, we have very different like storage systems in our customer sites, like also DDN and so on. So yeah, I know about this issue, but so far we didn't have any of these issues with this system because the metadata scaling is like really good, and even if users are doing some like bad metadata behavior, it was still performing well because we also, try to separate the CPU cores between data and metadata to have no overlap and so on. So far we didn't have any issues in this regard. Next one also, I understand you use direct I/O on the client side, but did you also force direct I/O on the storage server side? Yeah, the storage server side is only direct I/O, or not only direct I/O, but Lustre, if you use direct I/O, is also using direct I/O on the server side, and all Lustre-based caching and so on is disabled anyways for NVMe's. So there's basically no caching going on.
Okay, the following question I believe is for you because I'm too much a Xinnor employee to answer this question.
What made you decide to go with xiRAID for this project instead of other RAID or GPU-based solutions? So yeah, actually, if like there's MD RAID, which is like super slow and not suitable, especially if you do like parity-based RAID. It's like just way too slow. It's maybe good for RAID and OS disks, but that's about it. And then you also have GPU-based solutions where you have a dedicated GPU doing the RAID calculations for you. Performance is very similar, pretty much the same, but the issue is you lose PCI lanes because you have to put in the GPU somewhere. On top of that, if the GPU fails, you also lose your fast RAID calculation. So you're at another point of failure, basically, to your system. Because we need the PCIe lanes for the network anyways, because we somehow have to get all the throughput out of the server to the clients. We think this software-based solution is just a way better fit because xiRAID is also like very, very efficient. So if you do like full 180 gigabytes a second read or 80 gigabytes a second write to a building block, CPU usage is around like 20% or something like this. So it's not a lot because it's very efficient and using the AVX units on the CPUs. Yeah, so that's and the hardware RAID on the other hand. So if you have like a dedicated hardware RAID, Broadcom hardware RAID, it's just too slow again because you have then the PCIe bottleneck from your hardware controller. So that's not suitable for fast NVMe storage, in my opinion.
Okay, what is the core count suggested for a setup 24 NVMe?
I would say 2 times the NVMe count, roughly. So
yeah,
48.
Absolutely. That's what we pitch to our customer. To avoid bottlenecks, we recommend having 2 cores per NVMe drives. They're not allocated, but it's just to avoid bottlenecks. Yes, correct. 48 core per CPU.
And it's a single socket server. So we have 2 single socket servers with 48 cores in this configuration.
Okay, we clearly overrun, but I think we answered all the questions. So it was very nice to see all technical questions and make it a bit more interactive. So thank you everybody for attending. As I said, MEGWARE and Xinnor will be exhibiting at Supercomputing. So if you will be there, get in touch and book a meeting. And if you want to try yourself, you can always request a demo license, a free of charge demo license. And I'm pretty sure that MEGWARE will be happy to assist the customer in his territory for a proof of concept as well.
Yeah. Feel free to reach out via mail or on SC or wherever. Yeah. We also have for instance, we also have a test system in our benchmark center. You could test yourself if you want to. So.
Very good. Very good. So thank you so much. Have a wonderful day. Thank you, Markus.
Thank you. Bye-bye.
Bye.